linear algebra students. In this video, I'm going to be proving the spanning set theorem in Rn. Okay, so first of all, what is it? I just recalled you what it is. If you have a set of k vectors that are all in Rn, okay, and the last one of the vectors in the set, say the last vector, is a linear combination of all the preceding vectors. Then in this case, the span of this generating set is the same as the span of all the vectors from v1 to vk minus 1. Okay, how do you interpret this theorem? Look, there's no vk over here. In other words, if vk is a linear combination of the other vectors in the generating set, it can be removed from the generating set without changing the span of the generating set. Okay, and why is the proof important to watch? It's because it trains you in two aspects of proofs in linear algebra and sometimes even in mathematics in general. And the first of them, one concept that we will use to prove this theorem is that if we have two sets and we want to prove that they're equal to each other, we can do so by proving that they are contained in each other. In other words, we will first prove that the set number 1 is contained in the set number 2, and then we will prove that the set number 2 is contained in the set number 1. Okay, and that will prove that the two sets are actually equal to each other. And there's also another key concept that we will use in the proof that I will write over here. I will erase the green. Okay. And it is that a set is contained in another set if every element of set number 1 is also an element of set number 2. So let's actually write this down. Okay, so S1 is, a set S1 is contained in a set S2 if every element, so if every element of S1 is also an element of S2. Okay, and now let's get to the proof. Okay, so now I'm erasing this. Okay, so what we will do is we will label S1 and S2 to be each of these two sets. Okay, we will say S1 is equal to the span of V1. And actually, I'm going to go the other way around. I'm going to call S1 to be this set. Okay, with VK minus 1. Okay, so just to let you know, I'm going to choose another color. Let's say green. Green is perfect. So this set here is the set that I'm calling S1. And I will call this set S2. So S2 will be the span of V1, VK. All right, and the proof has two parts. The first part is to prove, so I'm gonna, there you go, is to prove that S1 is contained in S2, okay? And we're going to use that fact over here. We're going to take an element of S1, an arbitrary element, and we will prove that it's also an element of S2. Okay? So if now we have to set up another variable. Let's say U. If U is in S1, then remember that the span, by definition, is the collection of linear combinations of all of these vectors. So then U is a linear combination, let's say C1 V1 plus ck minus 1 vk minus 1 for some c1 ck minus 1 being real numbers, okay? Now remember what it means. It means u is a LC of the vectors from v1 to vk. All right, now I'm going to erase this. Okay. Then it means that u is actually equal to c1 v1 plus c2 v2, or actually let's just put all the dotted lines already, plus ck minus 1 vk minus 1. And now here's the magic trick. I'm gonna add in 0 vk. So the idea is that u is also a linear combination of v1 to vk, right? So it is also a linear combination of v1 vk with these weights, right? With weights c1 ck minus 1 0. And as a result, we just proved that S1 is contained in S2. So how am I going to do this? Yeah, okay, so I'm going to write in green this is S1 and this is S2. Okay. So now we have to prove the opposite. Okay, so this part is done. It was actually the easy part. Now we have to prove the opposite. So we have to prove that S2 is inside S1. Okay, so now we do the opposite. We consider U to be in S2, and it means that U is a linear combination, let's say C1 V1 plus CK VK for some C1 to CK in real. Okay? And now we will be using this. We will be using the fact that VK is a linear combination of the other vectors. So, since VK is LC of V1 to VK minus 1, it means that VK, now we will call the weights D. So let's say D1 V1 plus dk minus 1 vk minus 1. And then again, d1 to dk minus 1 are real numbers. So what we're going to do is we're going to take this equation of u and we're going to substitute vk in by this, right? So the vk that we have here, we will use this expression, okay? So that's what it's going to look like. So u is equal to c1 v1 plus ck minus 1 vk minus 1. And then we're adding this linear combination. So we have here ck. And now I'm just going to erase the no vk over here. Otherwise, it will get in the way. But then I'm writing d1 v1 plus, and finally, dk minus 1 vk minus 1. Okay. Now, what we're doing is we're using the properties of vector addition and multiplication by scalar. And what we do is we collect the different weights together. So, for example, if we collect the weights of V1, right, we have one over here, and we have one over here. So what we're going to get in bracket C1 plus CK D1 multiplied by V1. And then we continue like this. So we could do the second term if necessary, but actually I will skip that. And we will do the last term here with this. So what we have is ck minus 1 plus ck times dk minus 1. And this is all multiplied by vk minus 1. Okay? So as you can see, it is a linear combination of v1 to vk minus 1 with weights so I will just like underline them, C1 plus CK D1. Then you have a second one, C2 plus CK D2. And finally, we have that CK minus 1 plus CK DK minus 1. And all of these are real numbers. And this proves that S2 is contained in S1. Well, actually, that's it. It proves first that U is also an element in S1. And as a result, so I'm just going to write it over here, it proves that S2 is contained in S1. Okay. So it's a little bit confusing because look, it starts here. You have to read down and then back up and read this way. All right, now for the conclusion. So we proved that S1 is contained in S2 in step 1. And we proved that S2 is contained in S1 in step 2. So putting these together, it means that S1 is actually equal to S2. So in other words, the span of the k minus 1 first vector is equal to the span of the first k vectors. And keep in mind that this hypothesis, let's put it in red. So this hypothesis over here, okay, this was used in 2. And obviously this completes the proof. And here you are. So hopefully this first helps you to understand why the spanning set theorem in Rn is true. But you also have this idea of two sets being equal if they are contained in each other, and to show that a set is contained in another set, you have to prove that a generic element of that set is also an element of the other set. Here you go. I hope this was helpful, and see you in the next video.